So yes, my name is Mark Richardson. I'm the project lead at Bancor, and I'm going to be giving a generic presentation today. So this is much less about our products and a little bit more about information in the space that I think more people should be aware of or have a poor understanding of already. So we'll start with Sandwich Attacks 101. Who knows what a sandwich attack is or is convinced they know what a sandwich attack is? Or could you describe how one is performed? So I need to go over a little bit of notation before we get into the guts of this talk. And so this is notation that's borrowed directly from the white paper literature or the patent literature, depending on your perspective. And so here we have a liquidity pool, and it has two tokens in it, token 0 and token 1. And these could be ETH and wrapped Bitcoin or USDC, DAI, it doesn't really matter. And I'm denominating both of these tokens with X and Y and subscripting P to designate it as belonging to a liquidity pool. And then we have a user, and then they have a wallet that also has tokens X and Y, and I'm subscripting it with U to denote that this belongs to the user and not the liquidity pool. And then we use this convention that there is some delta XU that comes into the liquidity pool and gets added to its balance, and then some delta YU that is then returned to the user. So we're making sure that both of these numbers are positive, right? So these are in the reals, and the pool balance is always being having the delta XU added to it and having delta YU subtracted from it, and vice versa for the user. And so yeah, we're always using positive numbers in the reals, at least in these conventions, and there's more than one competing convention that you might see published elsewhere. So that's the end of the notation slide, and happy to get that out of the way very quickly. Now we need to describe the exchange model, and a lot of people are going to be familiar with some aspects of this, but there are going to be nuances that I think are probably new to you. So the most common, the canonical example, or the prototypical example, is the X times Y equals K liquidity pool, which was released sort of around the end of 2016. And there's two different ways that you can monetize a pool like this. And one is to collect a fee, which is very badly named, but is still the prevailing nomenclature in the industry. And you can do it in one of two predominant ways. One is that you can either subtract the fee amount from the user's input, right, from the DX amount, or you can subtract it from the DY amount. And they have slightly different calculations associated with them, and they're going to change the way that a sandwich attack is performed, and also how arbitrage is performed. So these are basically the two models, right? Or actually, this is the fee from amount in model only compared with the feeless amount. And if you compare them heads up, one of the things I want you to see here is that you can actually refactor this equation so that you basically have the pool's liquidity reserve in X tokens as just being artificially represented as if it's slightly higher than the amount that it actually has. So now we're no longer saying we're taking a fee from anywhere, but mathematically it gives you exactly the same result, and this kind of leads into some of the other criticisms I have about the words that we use to describe finances in DeFi more generally. So there it is. The feeless model is just XP there in the denominator, excuse me. And then on the left, we've just artificially amplified it by dividing it by a number between 0 and 1. And then the same is true if we're reversing that transaction. So instead of using f of dx, we're using f of dy. Okay, so that's the fee from amount in. Let's talk about fee from amount out. So again, here's the feeless model for a heads up, and we're going to compare it with the fee from amount out. Now, similar to the fee from amount in, we're going to adjust one of those token reserves by a small amount, but instead of making one of the token reserves look larger than it actually is, instead we're going to make one of the token reserves look slightly smaller. And again, this is exactly the same intuition as saying we're taking a fee from the amount that the user should be receiving in lieu of a particular fee being applied. But I still prefer to think of it in terms of augmenting a token balance. And so these are the two models that we have, right? Fee from amount in, fee from amount out. And then in general, the same notation applies. So we can, in any four of these cases, refer to the token that the user is sending and receiving from the liquidity pool the same way. And these are symmetric. So you can invert these calculations or swap the symbols X and Y and still get exactly the same formulas out. So that's the end of our exchange model. Let's see an example of a trade being performed. So a relatively simple example, we have a liquidity pool with 100 of each token and a fee of 0.3% or 0.003. And we're going to use the fee from amount in example to calculate this trade. And so all you do is take one of those equations that I've already shown you and start substituting in the values that are associated with the state of this pool. So we have XP is equal to 100, YP is equal to 100, and the little Greek letter delta is equal to 0.003. And after we process that calculation, we can see exactly how many Y tokens, or token 1, the user is receiving in exchange from the liquidity pool for the 10 token zeros that they are providing. Okay, now if we switch from the fee from amount in to fee from amount out, we get a slightly different result. So again, we're doing exactly the same substitutions, but now we're switching models. And what you'll find is that you get a slightly smaller amount in this particular fee model than in the last one. So if we compare, for example, the user state in the fee from amount in to the fee from amount out, what you'll see is that in the fee from amount in, they were given 9.066 tokens, whereas in the fee from amount out, they were only given 9.063 tokens, or 4 if you're rounding up. So they get a slightly better deal in the fee from amount in, which makes it seem like it's a better deal, right? Maybe this is the model that we should be adopting everywhere. But there is some problems with it, and I'm going to show you that in just a few slides. First, let's talk about sandwich attacks. So a sandwich attack takes a transaction that a user has already submitted against the pool and then rearranges it to get a result that allows the attacker to extract value. So this is exactly what it's going to look like. We take the example that we just processed, right? So these are the calculations that we just went through in the slides leading up to this one. And we're going to, imagine that the user performed this simulation themselves. This is an agreement effectively that they have with the liquidity pool. And so you might naively think that this is the result that they're going to get. But you can't make that assumption because the calculation is contingent on knowing the state of the pool at the time the transaction is actually processed. So in this particular situation, when a user is sending 10 tokens into the DEX smart contract, that's when the calculation occurs. And if that transaction hasn't been included in a block yet, then that means that someone can rearrange these transactions in order to extract value from it, and I'm going to show you exactly how to perform that attack. Okay, so this is basically how it's going to look like in the mempool, right? You have the user has 10 tokens in their wallet, and they've already committed to send them, right? That's the transaction that they signed. And we're going to forget about things like min returns and that kind of thing so that we can really explore exactly how sandwich attacks work. So it's because that state of the contract being able to change after the user has already signed it that enables this kind of attack to be performed. And you can perform it very precisely, but before we get into the precision of it, I'm first going to show you just a very basic sort of naive example of it. So here's the mouse, the one that's being preyed on, expecting to send 10 tokens in and receive about 9.06, and we're going to go with the fee from amount in model for this demonstration. Okay, so this is what the attacker does. They see that last row, right, the one with the star next to it, as the transaction that the user has already expected to commit to. And what they effectively accomplish is that they cut that transaction out of the block, and then they paste their own transaction before it, okay? So here we're going to, like I said, this is just a naive example of a sandwich attack where the attacker is just swapping the same amount as the user. The user's swapping 10 tokens, so I'm going to swap 10 tokens in front of them. I'm going to front run their transaction with the same amount. And then, only after the attacker's transaction has been processed by the liquidity pool, do we then let the user transact against that changed state in the liquidity pool. And because I control the ordering in the block, I have this flexibility to move the transactions around. So then we paste the user's transaction immediately after the attacker's transaction. And then we can just look here at the difference in the token output that they got from that liquidity pool. So compare the unattacked state to the attacked state. When no one was sandwich attacking them, they got 9 and a bit tokens, and now they're getting about 7.5, right? Which is a pretty dramatic change already. That's from the user's perspective. They're actually being charged almost 20% more on the value of the tokens that they bought, which is surprising. But that's not the end of the attack. So what we've done is we've excised the user's transaction, we've front run them, and then the sandwich is we then back run both trades together. So here, what the cat has done, right, the attacker, is that they've already received something like 11 tokens from the trade that they got out of the front run, and then they just dump everything back into the pool, right? They never wanted those tokens in the first place. So they then trade it back, and if you have a look at just their wallet state, and these are bundled transactions, remember, this happens atomically. So all they did was go from a wallet balance of 10 of token 0 to a wallet balance of 11.7. And they managed to do this completely risk-free, right? They got 1.7 odd tokens out of this transaction for doing literally nothing, okay? This is how a sandwich attack is performed. Now, what I said was that this is a naive case only, and what we should look at is what we refer to as the maximum extractable value, okay? So that's the MEV acronym that you may hear people throwing around without really knowing exactly what it means. So this is the challenge. Given that state of the pool, and given that you know that a user is trying to trade 10 of token 0 into that pool, how much should you front run with? And how much are you going to get after back running it? So let's go over that, okay? This is exactly the situation that's kind of made diagrammatic, and hopefully this video will live on YouTube or somewhere where someone can study it later for the details. But the information that we have, all the information that we have, is the state of the pool at the time that we're including it in a block and the user's input amount. You can get to a symbolic solution for this. And again, we're only going to be referring to the equations that I've already presented at the beginning of this talk that describe like 99% of the decentralized exchanges that you know about. And remember that these equations are symbolically reversible. Okay. So this is basically how you set up the equations. You know what the attacker's front-running trade should be in terms of its symbols, and I'm going to use the subscript A here to distinguish the user from the attacker, and remember the subscript P refers to the pool balance. So if we just take a look at whatever that trade is, let's say we don't know what it is yet, but we know that the attacker is going to get a certain amount of these DYA tokens out of that front-running transaction. And that DYA is immediately what we're feeding into the pool state that the user is then going to interact with. And then after we do that calculation, which is again just nesting some of these swap formulas together, we can then get the amount Y that the user is going to receive, which is what we then have to subtract from the pool state afterwards. And so we get this enormous nested equation, but it is symbolically compact, right? Everything that is in here will tell you exactly how the amount out from this transaction and from the attacker's perspective is related to how much they front ran with. And so after a little bit of work simplifying that, you can actually get it into a pretty well described and easy to follow form. And then all you need to do is take the derivative of this with respect to the amount that the attacker is sending into that pool. So, if you're going to do calculus, at least, let it be a derivative. So in this case, it's not too difficult. And so we can actually pack this equation down a little bit farther and just extrapolate all of the constants that we know that we're going to be working with. So in this particular case, after a little bit of extra work, we can substitute these A, B, C, D, E, F, and G constants for other constants that are associated with the calculation. And note that all of these remain constant from the attacker's perspective, right? After they're reordering this inside their block, all of these are already known, and this is not difficult to compute. You can get this in a few microseconds if you've got access to a normal cloud server or something like that. So after we've got that derivative, we want to set it to 0 because this is effectively where the attacker's profits are leveling out. which means that we can simplify this expression a little bit farther, right? The d constant gets canceled, all of it, everything in the denominator gets canceled. And so we end up with a relatively simple quadratic, and a couple of those constants get borrowed over from the rest of that calculation. Okay, and we only care, I should note, about the cases where the delta XA is greater than 0. Otherwise, the attacker is effectively donating money to the pool. Okay, and so that gives us an amount, 3,386, which is, I claim, the optimum front-running amount. This is the maximum extractable value amount. So let's go over what that example would then look like. We then have the user who is naively committed to send 10 tokens into the pool. An attacker comes in, front runs their trade with an amount 30 times greater than that, okay? Actually 300 times greater than that. And then the user's transaction is processed afterwards, and they only get 0.008. And then the attacker swaps back all of the 97 odd tokens that they got back into the pool to get 3396 tokens back out. Okay, so from the user's perspective, the price that they paid for the token is now increased by 110,540%, right? This is what a sandwich attack does to naive users, and this is why things like setting slippage tolerance is so important to keep it as close to 0 as you can. Because whatever you set the slippage tolerance to be, I can now adjust this exact formula to take exactly what it is you want to donate to me. If you set your slippage to 5%, I promise you I will take all 5% of what you set. Okay, now that was all from the fee from amount out. I mean, I'm not going to go through all of the details again, but just know that if the fee from, that was the fee from amount in. If we swap it to fee from amount out, you get a completely different equation that you have to resolve symbolically. But after you do that, what you find is that it's not quite as bad, right? The amount that the attacker can actually extract out of that transaction is reduced somewhat. And it suggests that the industry has actually set itself up to make sandwich attacks as profitable as possible, which is worth asking yourself who made those decisions, right? Why would, if you had the option to create a DEX with just a very simple code change, right? Instead of taking fee from amount in, you take it from fee from amount out. It's an interesting thing to think about, right? If you were designing these things, you would think that you might have a defensive programming mandate to make sure that naive users are exploited as little as possible. That in fact, the industry has gone the other way and made sure that when someone is exploited, it's exploited to the nth degree, sometimes hundreds of times more than how we made a slightly different design choice. And so that's comparing the two situations. So fee from amount in, which is what the majority of the industry uses, instead of getting 9-ish tokens, the user is getting 0.008. And if we switch to fee from amount out, it's at least 100 times greater than that. Something to think about. Okay, if you want to study these things further, I do have some additional text here that, again, I refer you to the YouTube recording of this if you want to dig into details. But I've also actually spent a lot of time digging into even more of the theoretical frameworks and potentially defensive programming strategies that you can implement to protect users against this. And I actually have developed, I run at a decentralized exchange that is actually sandwich attack immune, because it operates predominantly on users quoting prices rather than accepting the prices that the liquidity pool quotes to them. So that's the end of performing sandwich attacks. Let's talk about arbitrage. Arbitrage is similar in the sense that arbitrage is defined as being a risk-free trade, and certainly sandwich attacks are risk-free trades, at least from the attacker's perspective. But I think generally when we're referring to arbitrage, we're talking about two different pools being out of equilibrium with each other, and that you can process a transaction against both of them in order to extract value somehow. So let's go over that example just quickly. Again, we're using the same equations that I introduced earlier in the talk. We're just going to process a trade against the yellow pool to get delta y 0, and then we take delta y 0 and feed that back through the blue pool in order to get a different delta y. Or in order to get delta x back. So again, we can nest these together, and again, going through some algebraic rearrangements here, which can take you a little bit of time, but at the end, you get to effectively this result. And I haven't optimized this. This might pack down a little bit farther, but I really like the idea of having this huge equation streamed out along the top of the screen. And this is what you get by evaluating the derivative of this at 0. And so that tells you exactly how much you need to swap against these pools in order to bring them back into equilibrium. And after you've done that, what you will find is that you get an amount of tokens out of this for free, right? So all I've done is buy tokens from one pool and then sell it to the other pool. And now I'm up 4.6 tokens that I didn't have before. That's it. And I can, again, do this atomically. So there is no risk to performing this transaction. So that's how you perform arbitrage. Who did that value get extracted from? Okay, and there's a very deep misconception that I think a lot of commentators in DeFi talk about, which is that arbitrage trading extracts value from liquidity providers. Okay, this is generally how it's sold to us. And this is the misconception. I'm going to show you exactly how these arbitrage opportunities arise and then who is actually losing out in some of these things. So this is actually what happens. If you have these two liquidity pools and their prices that are at equilibrium with each other, and you have a naive user who trades on one of these pools, let's say via the front end that the DEX gives them to use. After they have traded, the market then falls out of equilibrium, at least with respect to these two different pools, because they didn't use trade routing or aggregation in order to keep these things trading fairly. And that difference, right, how much they pushed that market out of equilibrium is exactly the amount they overpaid by, right? This is the trader, no one's making them do anything, tricked into paying more for those tokens than they otherwise would have been able to achieve had they used something like 1inch or ODOS or something to correctly route those trades. So this is the demonstration, right? The user has overpaid by not using all of the available liquidity. Now, the arbitrageur can come in and do something. And it's not, it's not malicious in nature. All they have done is notice that there are now two pools out of balance, and they then bring them back into balance by trading against them both. And that means that they're now quoting the same marginal rate, give or take, and they get to extract a little bit of value from that process. So the overpaid amount is basically equal to whatever the arbitrageur is extracting. And liquidity providers do not lose any value here. And there's an elegant proof for the fact that liquidity providers don't lose out from arbitrage trading by considering the fact that arbitrage gets closed all the time by people who aren't arbitrageurs, right? Or who don't actually extract any value from the system. So consider that these two trades may be performed by different people. So in the first instance, you have someone trading 18.8 of the X0 token against liquidity pool 1. And then in a second trade, someone completely different, who isn't in collusion with the first person, trades in the opposite direction, is trading 60.5 of the Y tokens back on liquidity pool 2 to get some of those X tokens back out. Here, the market is still going to be put back in equilibrium. And in effect, they have arbitraged the system, but no one has extracted any value from anywhere. It's just that these two different users have now identified better trading opportunities, but they have no interest in closing the arbitrage themselves, but without knowing who each other are, have still managed to close an arbitrage. And so if the outcome is the same, then it doesn't matter who's doing it, right? Arbitrage isn't something that is being done maliciously to a liquidity pool, it's just something that happens. Okay, and it's generally the result of the trader who caused the market to fall out of equilibrium that's losing the value. The liquidity providers don't lose any value at all. So that's the end of the misconception. If you would like to know a little bit more about how to perform complex arbitrage, right? So beyond the symbolic examples that can be performed algebraically, we've recently published a paper to the archive called Marginal Price Optimization, which is competing with another industry standard called Clarabelle, which is a convex optimization-based algorithm. And our model is about 200 times faster, is significantly less computationally, has significantly less computational overhead, and can be executed against any number of DEXs simultaneously, which is really helpful. So a little bit about me. I currently run the project Bancor. And the product that we've built that runs decentralized exchanges now on Ethereum mainnet and a whole bunch of other places is called Carbon DeFi, which is an order book style DEX, doesn't have the same kind of vulnerabilities to the attacks that I've demonstrated here. If you would like to discuss with me anything I've presented here, or anything else that you might like to discuss in DeFi decentralized exchange, you can reach me at Telegram. Is probably the easiest, but please be patient with me as I get a lot of messages. My Twitter handle is here. I generally don't respond to messages there. The email is a very good secondary source of contact if Telegram fails. So thank you so much for being here. I thought that this was, I hope that this was informative and that you learned something and maybe even enjoyed it. I hope that you're enjoying the conference, and thank you for your attention.
So much, Mark. Amazing presentation and a great deep dive.